This talk is Kubernetes after 18 months, and what I'm going to kind of focus on is I'm Thomas Stevens. I'm at UStudio, and I'll get into what we do in just a second, but the focus of this talk is kind of just like the story of us using Kubernetes, what worked, what didn't work, how we fixed the things that didn't work, and where we are now and how we liked it. So who are we? We make video easy, although I don't think that's the tagline on our banner. But we are an enterprise video platform, and we make it easy for people to manage and distribute videos, mostly large kind of corporate customers that have a lot of videos, and mostly customers that want to integrate video into other systems like CMSs, CRMs, LMSs, other TLAs. We have a small development team, and we do everything API first. And that's kind of what enables us to integrate with other systems. And we try to do things like kind of the best way we can, pragmatically speaking, because we are a small team and we can't spend lots of time planning things, but we try to do our best. And we're DevOps because we don't have an ops team, so that makes us DevOps. I am a full stack developer at UStudio. And we're mostly full-stack developers at UStudio. Again, small team, that's what you get. And that's my GitHub, if anybody's interested. So our application is a single instance, multi-tenant SaaS application. It runs in the cloud. It was built from the ground up to run inside the cloud, but in what I sort of, in air quotes, call the traditional cloud, because it's like an old thing now, which is just, VMs, provisioned with Puppet. We use Fabric and libcloud to kind of create the instances and then execute the Puppet commands to deploy things. We had a kind of a deployment infrastructure that's pretty good in terms of like, I have some code and it's ready to go and not much changed, and I want to ship it to stage. There's like one command, it goes to stage. QA says it's good, there's one command, it goes to prod. That was pretty good. The thing about it is there was a lot of stuff that happened every time you ran that command, and we had to maintain that because we wrote it all. So things kind of like kept getting worse. Not worse, but like there'd be this problem, and like every fifth time this thing wouldn't work, and it was just like a nightmare to fix the problem. It would take us 2 weeks to fix this sort of intermittent failure, and then the sales team doesn't want us spending all of our time fixing our deployment tools. They want us like shipping new features or whatever it is. So we started like looking around, and we started sort of attacking individual pieces of the problem. Like we need to fix how we package our application. Maybe we should use Debian packages, or Puppet is sort of not working that well for us. Maybe we should be using Ansible or whatever it was. And we just never had a whole lot of progress because each thing would only fix like a tiny little thing, and it just wasn't worth the effort to kind of, it wasn't worth the effort because it wasn't fixing enough. So eventually we were really kind of struggling because we wanted to start breaking things out into smaller services. And every time we wanted to break out a service, it was just like a couple sprints just to get like VMs and a database and all of those sorts of things you need for a service. And so we really needed to solve the problem. The other thing we wanted to do is we wanted to sort of explore new cloud vendors because we've always sort of built the application to work across cloud vendors, and we wanted to sort of make sure that it actually did. So we chose Kubernetes. It's supposed to be angelic voices here. The reason we chose it is because it sort of solves all of the problems we had kind of at the same time, or almost all of them. So you get packaging and distribution because there's Docker images. It's vendor agnostic. We really liked the fact that it wasn't like, Heroku isn't quite the same thing as Kubernetes, but you build your app and you have like your proc file, and it only works in Heroku. It has application configuration and service discovery built into it. It kind of manages the deployment lifecycle of like, you've got new code, you want to start standing up instances for the new code and stepping down instances with the old code and make sure the application doesn't go down in the meantime and things like that. Unlike something like Heroku or more of like a platform as a service, it has the flexibility to do different things. So we don't have to change our code too much to work inside it. If if your application works in the cloud now, if it works in AWS or Rackspace or Azure or Google on a bare VM that can disappear at any time because it's a VM, then you can probably get it working in Kubernetes relatively straightforwardly without having to change it too much. And then it's also sort of like production ready. We started using it around 1.2, I think, and we felt pretty confident that not only has it been used by some people and it's gotten some good testing and we feel like we trust that it works, but also the community is still growing around it and they're still adding features, and that was an important thing for us. And this is like my favorite part about Kubernetes, which is that when you're using Kubernetes, instead of like deploying your code to the servers, you're deploying your application to production, or hopefully stage first. Like as a developer, that's what I want to do. My job is to deploy the code, my application to production. I don't care about getting my Python source files onto a server somewhere. That's kind of not that's not the level I want to be thinking at. So real quick, I'm not sure how many people know too much about Kubernetes. How many people feel like they understand all of these words in the context of Kubernetes? Okay, how many people feel like they need, maybe they don't understand a couple of them? Okay, so just real quick, and I know there's some like intro to Kubernetes talks too, so I don't want to overlap too much, but a pod is like a virtual computer, and it's composed of containers. Containers are Docker containers. Each container has a single sort of root process, and usually that's the only process. It actually can fork and stuff. All the containers inside a pod think they're on the same computer. They can talk to each other over localhost. So from a networking perspective, a pod is like a computer, and a pod has an IP address that all the other pods can use to talk to it, just like they were little computers. But they're not little computers, they're just little containers, and there's all sorts of IP tables magic happening. Deployments, jobs, and stateful sets, these are things that manage your pods for you at a high level. A deployment is just an application that runs more than one instance. A job is something that runs to completion and then goes away. And then a stateful set is, if you need to run a database inside Kubernetes, you need a stateful set. Config maps and secrets are kind of what they sound like. It's just a bundle of key value pairs that you can expose into your application. Secrets are just secret versions of config maps. And then a service is like a load balancer. So a service is listening on one or more ports. It gets an IP address. If you're running inside a supported cloud vendor, it actually gets a load balance. Like if you create a service inside a Kubernetes cluster running inside AWS, you actually get a load balancer, like a elastic load balancer instance that maps to that service. Services direct traffic to pods, just like a load balancer directs traffic to VMs. One interesting thing about services is they run at layer 3, meaning they're running at like TCP, at the TCP or UDP level, so you can't do things like you do an Nginx where you're like, oh, if the URL that the person is accessing is this, send them here. Otherwise, they don't know HTTP. They only know I got packets and I'm going to send them here. So we picked Kubernetes and we needed to get started. We had a kind of an initial project. It was a new project. It was relatively small. It kind of had a focus sort of end date to it. And so we sort of picked that and we decided to go with it. There's actually a step 0 to this. Don't try to run a database in Kubernetes unless you really know what you're doing. We kind of looked at, we were running our own databases inside our cloud vendor, and we sort of looked at, well, it's not one server, it's like 3 servers because you don't want the one server to go down and your application to go down, and you want like redundant data, and you want hot failover, and you want to be backing up your data, and so then you're putting them in some sort of object storage, and that costs money. And we looked at how much we're actually spending, and then we looked at sort of SaaS providers, and we were like, oh, these actually aren't as expensive as they look. So if you're considering Kubernetes, I would say definitely consider SaaS databases because you'll save yourself a lot of heartache. Or alternately, I know a lot of the Kubernetes people will talk about, if you're running Kubernetes inside like a data center, people will say, keep running your databases the way you've always been running them. Don't use Kubernetes for that, use it for your applications. But you can do it. if you really want to. So our first step was this. This, if you actually go find the script inside the Kubernetes repository, it's got all these warnings about how it's deprecated and you shouldn't use it anymore. But at the time, a year and a half ago, is kind of how you got started. So there's a lot of settings you can change instance sizes, change security settings, and stuff like that. So we kind of changed things, and we ran the script, and we got a cluster up. And it was using like auto-scaling groups and stuff, so if a node went down, it would get recreated and things like that. So it kind of got us into like a decent state of like Kubernetes is working. The other thing is we needed it to be sort of production grade for us. What that means is the nodes are getting monitored, so we get alerts if they run out of memory or they go down or whatever. And then any applications that are running inside their logs get slurped into a log aggregation service. We use Datadog for the first thing for server monitoring, and we use Sumo Logic for log aggregation. And these are really easy to integrate with Kubernetes. They both, now anyway, they both have just sort of copy paste. You do this, you run it, and it works. So if you use those, look it up. If you use a different one, Google like my log aggregation service space Kubernetes, and you might find somebody. The way this generally works is a daemon set, which I don't actually have on the previous slide. A daemon set is a pod that runs once on every server, and it sort of lets you get access to sort of actual server level things if you need actual server level things. Which you mostly just need for management. We haven't really had this is an application and we want to run it as a daemon set that we're developing. So the first thing is building a service. So we just sort of created an empty repository. It had a main function, a main file. It had a package that, pointing at my notes, not that, had a main file, had a package. We use Alpine because it is smaller, and so your things can spin up faster. You can deploy new code changes faster. This is pretty simple. You don't have to mess around with virtual envs because you only have one thing inside this Docker file, so you don't have to worry about dependencies bleeding between projects and stuff like that. The other kind of cool thing about it is you're always packaging your applications the same way regardless of what language they're written in, so you don't have to have like virtual env, and then you've got bundler, and then you've got your package JSON, and you've got whatever. It's always kind of the same, which is nice. Another thing you can see, this is Python 3. This has been really helpful for us to migrate to Python 3. We can write our new applications in Python 3. We can port smaller applications over to Python 3 as we migrate them into Kubernetes. And we didn't have to write any sort of, on this server, we need to have Python 3 installed, and so go write the Puppet code that installs Python 3. So it makes it easier to sort of slow roll that transition for us, which we found to be helpful. The other thing, then the next thing is, okay, so you've got your application, it's running in a Docker container, a Docker image. You need to tell Kubernetes how it works. There are these YAML files. This is an example of the very beginning of a YAML file. The way we decided to do this is all of our deployment configuration is inside the applications repository. We have, by convention, just a subdirectory called deployment, and that's where all the YAML files go, and we've got some other stuff in there. When we were using Puppet, we had a single shared repository of all of our Puppet code, and it let us share code between projects nicely because it was all just right there. But the problem is then every time you need to change application configuration, you've got a pull request against your application that adds a new configuration, and then a pull request against the Puppet repository that adds the new hooks into the configuration, and that's kind of obnoxious. And so our sort of hope was that's not worth the effort, that's not worth the benefit, that effort isn't worth the benefit of sharing code, and hopefully with Kubernetes there won't be a lot of shared code because it'll just be simple and we don't have to write a lot of code. So that was our goal there. SSL termination, this is something that you have to get working if you want SSL termination, which you do. There's at least two ways to do this. The first way is, and this is kind of the old way, although it still has some advantages. It's called, they call it an Nginx sidecar container. So like I said, a pod can have multiple containers inside it, and they all talk to each other on localhost. So in one of our application pods, we'll be running our Tornado application here, and then we'll be running Nginx also. So there'll be a single version of Nginx that's talking to a single version of Tornado. Nginx is doing the SSL termination. Nginx is also sanitizing the HTTP requests and stuff like that. If you read Tornado's documentation, they say never expose Tornado directly to the open internet, and this sort of prevents it. A service is just how you do load balancing, so there'd really be like a bunch of these. And then the cloud, the internet, is talking to the service, talking to Nginx. I kind of took the arrows off because they started making the picture hard to read. But the arrows go like that. It's a little bit inefficient because you're running, like for every Python process, you're running one Nginx process, which is not exactly how Nginx is intended to be used, but it's not a very heavy tool, so it sort of solves the problem. There's a newer thing called an ingress controller, which will actually configure like a layer 7 load balancer in your cloud if you're using a cloud that supports it, and if you're using a cloud at all, because if you're running Kubernetes inside your own data center, you don't have a cloud. And the support for them is kind of spotty in different vendors, and then they have different, some vendors will have like full feature support, like Google has like everything works, but then other vendors won't necessarily have everything working. So if you're using an ingress controller, you have to kind of be careful that you're probably not as cloud agnostic as you would like to be. And then the other thing is we wanted end-to-end encryption. If you have the ingress controller doing your SSL termination, then you need to be able to configure it to like re-encrypt the traffic back to your backend, and then you need a private key, like a private self-signed certificate, and they don't all support that, and it gets complicated, and you definitely want all your traffic encrypted all the way to the server. So the next thing we needed to do is we needed to be able to configure our application, and we had some requirements for this. For storing the application configuration, we wanted a central repository that was sort of like the value of record. We wanted to be able to control access to it so we can grant people permission to access it, revoke permission, change the values, et cetera. We wanted it to sort of be backed up and encrypted and all of these things because these are secret values. These are like keys to services and stuff like that. We knew we wanted to, in general, set configuration values into our application via environment variables. And then we were really looking to not run another service to manage our application configuration. Because the point of this was to run fewer services and manage fewer things, not add to things that we were managing. So what we ended up using is, we actually use our password manager for number one. We've got sort of like an enterprise password manager that lets you do a lot of fancy stuff in terms of encryption and access control and whatever. And then what we do is we have automated scripts which take the values and they turn them into Kubernetes secrets. The nice thing about Kubernetes secrets is that it's really easy to expose them into your application. I'll show you how on the next slide. And we just sort of automate that transition. The password manager doesn't have to be up for the applications to run. They're not talking to it. They're just getting their configuration as environment variables. So it's not like this thing that we have to monitor and make sure it doesn't go down or our application stops working or things like that. So this is how you get this is one way to get your configuration into your application. This is a snippet from inside a YAML. You say, in this container, I want to set environment variables. This is the environment variable I want to set. I want to read the value from something. The thing I want to read it from is a secret. The name of the secret is this thing, and then because secrets are like bundles of key value pairs, you say, the key I want to read the value out of is this, and then whatever value you've set becomes the value of this environment variable. So that kind of got us started. It's pretty simple. The problem is that as you're first developing your application, you're going to keep adding more configuration options because first I just need to configure the database. Okay, that works. Okay, now I need a Redis configuration because I want to cache things. Okay. Oh, and now I'm like talking to this other service and I need to configure how I talk to it, and it sort of grows. And every time you do that, this YAML file changes, and that means it takes more effort to sort of deploy your changes out to production. What Kubernetes is doing under the covers is it's keeping, when you give it a YAML file, it's keeping inside its etcd database representation of this YAML file. And when you run a tool like kubectl, if anybody's used kubectl, that's how you talk to Kubernetes. What you do is you say, here's what I want it to look like. And all it's doing is it's sitting there polling, and it's saying, what's it supposed to look like? What does it look like? What's it supposed to look like? What does it look like? And if it ever doesn't look like what it's supposed to look like, it changes it. And so what that means is this YAML file, which you've probably checked into your GitHub repository, is duplicated into your Kubernetes cluster. And what a deployment means is a deployment is you sort of copying the latest version over into the cluster. And so you want to make that as painless as possible. If you keep having to add environment variables or remove environment variables, you're making those changes complicated. So that kind of slows things down. So we changed how we did it. So the first thing that we did is now we don't store a key value pair for every sort of configuration point. We store a shell script. We call it environment sh. And inside it, all it does is set a bunch of environment variables. Export the DB endpoint to my cloud scale NoSQL database. The secret key is 12345. Don't do that. It's kind of secret. An idiot would put on his luggage. So then what you can do, secrets you can expose secrets as environment variables. You can also expose them as volume mounts. What that means is you can say, take this secret. I want this secret to exist inside my container as files on the file system. So here what we're saying is I've got some secret, and I want inside app/secrets on the file system, I want a file, and the name of the file is the key of the secret, and the contents of the file are the value of the secret. And then all we have to do is inside the Docker file, instead of just directly starting Python, we first source the environment sh file that sets all the environment variables. Then we execute Python. All the environment variables are set. If we add new environment variables, we just have to change that file, but we don't have to change our Kubernetes configuration. Makes things go a little simpler. Also, we're using a semicolon here instead of a double ampersand for a reason. It's so that if you really need to run your application outside of Kubernetes but inside Docker, it just sort of works, and if it has built-in default values, it works. So that was sort of how we fixed that. The last thing is we needed to be able to deploy things locally so that we could test our changes before we opened up pull requests and sent things to stage and et cetera. So we ended up, we weren't going to have a shared repository, but we have one. We call it full stack, and it just has a bunch of the automation scripts inside it. Has no actual things that are specific to any of our projects. And then what we do is we create symlinks from inside it out to wherever we have the project checked out. And then we can do things like the start service script, which you say start service dev my project, and it goes and it finds all the YAML files, and there's some hooks for adding shell scripts before and after and stuff like that. And it just like stands up your service, single line. It's very handy for managing. The first time you check out a project, you can get it running pretty quickly. Another thing that we do is, I don't have a slide for this, but Docker images have tags on them. And usually the tag is the version number. Inside our GitHub repository, when we check, the YAML file references the Docker image. It says this container uses this Docker image, including a tag. Inside GitHub, the tag is always latest, which is just the last build that CI ever did. We never actually use latest inside stage or production. You don't want to just sort of, a pod dies and it spins up a new one, and now there's a new latest and it hasn't gone through QA, but congratulations, it's running on production. So instead what we do is inside GitHub, you can just easily spin up the latest version of whatever, because you probably don't, inside your local dev environment, you probably don't exactly care, or you definitely want, or if you care, you probably want the latest anyway. But inside production, before we deploy the YAML file to stage or production, we'll set the tag to the build number we actually want. And that's how we can, inside CI, we do a build, we push it into our Docker repository, we go to the stage cluster and we say, okay, make the image, build 23, QA tests it, it's good because we're awesome, and we never write bugs. So then we go to the prod cluster and we say, okay, the tag is build whatever number I just said, I already forgot. Anyway, that was it. we got it working. It worked. It was pretty cool. We had services running inside Kubernetes in production, and our customers were really using them. It was pretty sweet. Just a real quick kind of diversion. About a year ago, Oracle came to us, and they had a new product that they were rolling out that at the time was called bare metal, but I think it's just called Oracle Cloud Infrastructure now. And they were interested in what sort of a video processing workload would look like on that. We knew that it would be difficult to port all of our Puppet and Fabric and libcloud code over to like provision things inside their cluster. We hadn't actually ported our video processing application to work inside the service, the part of our application that does the actual video processing. Hadn't actually ported that over to Kubernetes yet, but we thought, you know what? It might actually be easier to just figure out how to run Kubernetes on this thing and then get our application running inside Kubernetes and then run it. And it actually worked. We were able to do it in just a couple weeks. At the time, there weren't sort of products that we could use to just like stand up Kubernetes very easily in a kind of custom environment like that. And it was all pre-release stuff too. So we had to read the Kubernetes the hard way talk, and I had to set up Weave to do networking. And it was, I had to screw around with IP tables, which I haven't done in a long time. And even then, I wasn't good at it. But we got it working. So it's kind of an interesting, it was actually easier to figure all of that stuff out, take the application, port it, and get it working inside Kubernetes than to port our Puppet code to a new operating system and cloud vendor. So that was sort of a positive. Okay, so we had the cluster. It was working. It was up. It wasn't going down. People were really using it. We were adding services to it. But there are a couple things that were hard about maintaining the cluster itself. We didn't really have a procedure for upgrading the code easily. Adding and removing users was like SSHing into boxes and things like that. It was just managing Kubernetes itself. While normally it kind of doesn't go down and it just runs and you don't have to think about it, you do have to think about it. You do need to upgrade Kubernetes. You do need to, add and remove users and stuff like that. And so we kind of looked around for what's something that solves this problem for us, because again, we're trying to get out of the business of messing around with this stuff. We looked at a lot of stuff. There's tools that you can like sort of hit a button and it spins up a Kubernetes cluster. And what we ended up settling on is a SaaS, like a service that runs Kubernetes. We use Google Container Engine, but there's a lot of options out there. Obviously, Google Container Engine only works in Google, but there's others that work kind of elsewhere. There's others that you kind of run yourself. There's some that they run for you. There's a ton of options out there, and I kind of highly recommend considering that if you're looking to get started in Kubernetes. They solve a lot of problems. Another thing we wanted to do is our original cluster, we had a namespace for stage and a namespace for production. And we sort of did that because we weren't sure if it was going to stick, and we didn't want to spend a ton of money on multiple clusters and stuff like that. So that's kind of what we decided to do. As we sort of felt more confident in it, we said, look, we really want to isolate stage from production. We don't want the workloads interfering with each other. We want to be able to sort of test and upgrade to Kubernetes itself inside stage and then make sure it works, things like that. So we created separate clusters in stage and production. And then we, in Google, we actually have a separate project for stage, a separate project for production. And then we have a third project where all of our Docker images go. And then they each have a service account that gives them access to that. But so anyway, there's a shared private Docker repository with our Docker images in it. The first thing we decided to move to this new cluster after we got it, and that was like you click a button and you get a cluster. So there's nothing really to talk about standing that up too much. The first thing we really wanted to move was our video processing pipeline. We knew it would work because we'd just done it in Oracle, but we knew it has some challenges in terms of, there's sort of two things about it. One is if a video processing job dies, we can restart it. It's not that big a deal to restart it, other than the fact that if it was running for an hour and 59 minutes and it was going to be done in 1 minute, because it's a 2-hour long job, and then the node dies because somebody like like, oh, I'll go upgrade Kubernetes this afternoon, and it kills this job, and now the user has to wait another 2 hours for their processing job. They're not going to be super happy about that. So we wanted to kind of isolate the management of these sort of expensive tasks. And then the other thing is we wanted to make sure that if somebody dumped a bunch of video processing work into the queue, it wouldn't affect sort of serving web requests and stuff like that. So the way we solved this is with node pools, which is a feature of Google Container Engine. But basically, you can have you can sort of define pools of nodes, and you say these nodes are this size, and I have this many of them, and you can, if you want to scale up, you just change the number of nodes, or if you want to scale down, vice versa. But then the other thing you can do is you can set labels. So inside Kubernetes, everything is a resource, and any resource can have labels on it. The actual physical nodes that Kubernetes is running on have a resource that gets like shadowed into the Kubernetes structure, and they can have labels too. And when you define a node pool, you can actually define custom labels that get applied to just the nodes in the node pool. And then when you define a pod, you can say, I want this pod to only run in nodes that have labels like this. People use this for like, another thing people will use it for is they're using TensorFlow and they want to do GPU processing, but they don't want every single node to have a GPU inside it. You can define a label on the nodes that have GPUs available, and then if you spin up a job that you want to guarantee it has a GPU, you say node selector, node of the GPU. But we use it to sort of separate workloads out. We started with 2 node pools. We have sort of a stateless node pool, which are applications that are normal RESTful, or not RESTful, but normal sort of stateless web applications. And then we also had, we call it the stateful node pool, which is just things like the video processing that are expensive you don't want to just die randomly necessarily, if you can avoid it. We also added a real-time pool, which we use for live processing. It doesn't enforce any real-time guarantees, but it does allow us to sort of isolate that workload and make sure that like batch video processing jobs which can run slower and nothing too terrible happens, don't interfere with live processing jobs, which can't run slower. So we sort of finished that. We started moving our stuff into the Google Cloud for our new cluster. We still had our old cluster up, and we still had our old VM sort of traditional cloud cluster up. And it turns out that when you're running your application across 3 different cloud vendors, this happens a lot more than it happens when you're running it inside one cloud vendor. For the most part, this isn't a problem. We sort of build the application with the understanding that even within a data center, the network will go down. One thing that we found, though, is that there's a lot of libraries that don't enable TCP connection or read-write timeouts by default. So you could sort of like make a connection to this service. The network was down when the connection was open, and it just hangs forever. So we had to go in and sort of figure out inside every library, how do you change the TCP connection settings before you connect to FTP or whatever? The last thing we wanted to do is we wanted to move our core API into Kubernetes. This is something that, well, we have a lot of sort of small independent services. They tend to be sort of like for this feature or that feature, and they're sort of back-end things that nobody talks to. Everybody talks to our API. Whether you're using the UI or using integration or you're writing your own integration, you're probably talking to the API, and you're probably talking to the one API. And we wanted to move that. And we wanted to move it without it going down. So kind of the first thing that we had to do is the API had a lot of cruft associated with it. Things like we were serving our JavaScript source files for our single-page apps off the disk via Nginx on the API server. Well, there's no API server. We don't really want to have like a Docker container that has 2 apps, like the web app and the app in it. We want those to be separate things, so we migrated to serving them off a separate DNS entry, making those served by object storage, putting a CDN in front of it, things like that. There are some other services that were sort of, they were sort of running around the API, but not in the API. And those needed to get moved to Kubernetes also. The key here is we didn't do this all at once. We said, okay, we're going to spend a sprint and we're going to move all of our static files to a CDN and serve it off a different domain. Okay, now we're going to spend a week and we're going to take this little thing and we're going to get it ready to go in Kubernetes. And every time we did that, the core app stayed the same, and it just started talking to another thing that wasn't in the same data center as it was until we just had the app, and that was all that was left, and then we could move the app into Kubernetes. And so we did that, and it worked relatively easily. Another thing is that as we were and there's actually one thing that didn't work well, which I think is in a couple slides. One of the things that Kubernetes gives you is every service gets a DNS entry, and so you can, if you know the name of a service and you know its namespace, you can talk to it and you don't have to configure what its IP address is or anything like that. It's a pretty cool thing. We wanted to talk to these services over HTTPS. Initially, this wasn't a problem because, 9 times out of 10, we had service A in one of our data centers and then service B in a different cluster, and so they couldn't talk to each other internally anyway, so we just had a public DNS record. It has a publicly signed SSL certificate, no big deal. Once you need to start talking over those internal, the names are like, this is an example, right? So for like our live streaming namespace, they'll be like foobar.livestreaming.service.cluster.local. This is not something that you can go buy a DNS or an SSL certificate for, obviously. So this is the thing I was pointing at. So what we did is we created a root certificate, and the root certificate we store in a secret place, encrypted and everything that needs to be done. And then every time we create a namespace, we create 2 secrets inside that namespace when we create it the first time. And this is all automated with a script. We take the public key for the root certificate and we put it inside a secret. And then we generate a new certificate that's signed off of star dot whatever the namespace is, dot service dot cluster dot local. And we sign that against the root certificate. So there's this shared root certificate that's internal to us. And then every namespace gets its own star certificate hanging off of it. On the server, this is an Nginx configuration. Nginx, if you give it 2 servers that have SSL turned on, that have different server names, it just automatically starts using SNI, which is a way for a server to give you back different certificates depending on the host header that you sent. So basically, if you have some server and it's hosting at 5 different domain names, a single Nginx instance can serve you the right certificate based on the way you talked to the server. So that's what we've done here. Internally, we're using the local certificate. It's not self-signed, it's signed off of our internal root certificate. And then, but if the connection is coming externally, we use our public, signed certificate. And then what we do on the client, we're starting to do a lot of stuff at application startup, so we created a script called entrypoint.sh, and inside the Docker file, all we do is say, the entry point is this shell script, and then it has stuff in it. This is kind of the key thing here for SSL, which is that we take the root public key and we add it to the operating system's list of like valid public keys. And the nice thing about this is our application code doesn't have to be changed to go load it up into Python's SSL context. Or the alternative would be turn off SSL validation, which is not a great idea. And then you can see we kept in the environment.sh stuff inside here. One more thing that we did, our core application does not read things via environment variables. It reads things via a configuration file, which is actually like a Python file, and it has actual Python code in it, not just key value pairs. And I could give a talk about why that's not a good idea. But so we, it's not that big a deal actually if you're using configuration files. You just make the file one of your secret values, and then you mount it, and then you somehow get your application to point at it. For our application, I think we do it 2 ways. One of our applications, it only ever looks for it in one place. So at the beginning, inside the entry point script, we have to go copy it into the place that it's looking for it, which is conveniently right next to the code instead of in a nice folder that we could mount. And then the other way is with an environment variable. So then we just sort of statically set an environment variable. We had one kind of big problem when we moved, which is that our API server was running a lot of instances, a lot of pods, and every time we deployed, it would take a really long time, like 45 minutes long, and it would, not the whole time, but sort of intermittently drop out. And so we needed to fix that. So the first thing we did is we wanted to stop it cleanly. So I actually have Python code here. This is a way to stop Tornado cleanly. You have a signal handler. When Kubernetes decides to kill a pod, what it does is it sends a sig term, which is the please stop now, and then it waits 30 seconds, you can change it, and then it sends you a sig kill, which is the I'm not waiting for you anymore, you're dead. And so what we were just sort of letting the process happen, and then it takes 30 seconds for the application to stop before it spins up a new one, and it was kind of, we felt like it might be overloading the system. So here we listen for a sig term, we stop the IO loop, and then we stop the server immediately. So what that means is Tornado stops accepting new connections, but the IO loop is still running, processing open connections. And then we wait 2 seconds, and then we say, okay, anything that didn't finish in those 2 seconds, it's too late. You're dead. Tornado doesn't give you a good list of all the open sort of pending things on the IO loop. It can give you sort of promises that haven't been resolved and things like that, but it's not complete. And so this is some Python code that would accomplish that for you if you use Tornado. The other thing is we were running a bunch of other containers, and some of those containers were running applications that actually listen for sig term, and they were just immediately exiting. And if our Python code talked to that process to do something important, when it died, everything would stop working. So we had to tell it to sleep for 2 seconds before actually dying. Kubernetes has these lifecycle hooks, which are like sort of things you can do before or after a lifecycle change. Lifecycle is like starting, running, broken, terminating, it's really gone, which isn't a lifecycle step, it's just gone. The other thing is it was taking a long time for the application to start up. We have a lot of Python files, and we could tell that it was just between we added a log statement to the script saying we're starting Python, and then we added we're in main, and it was 10 seconds. So we do this inside our Docker file. After we sort of copy everything in, we compile everything. This generates PyC files, and so it cut that startup time down. Those made things better. It didn't make everything perfect. It turned out the sort of fundamental problem is at the height of a deployment, we would have about 65 pods running on a single node. When you do a deployment, it starts standing up new pods and starts shutting down old pods, and so there's this period of time where you have more than the normal number of pods. And we were sort of Kubernetes is supposed to handle 100 pods at a time, and they test every release. They have a bunch of tests that sort of prove that it can handle 100 pods at once. Turns out those are very simple pods. When you have 5 containers inside the pod and they all have lifecycle hooks and readiness probes, can't actually handle 100 pods. 65 was over the limit. So we added more nodes, and that kind of solved the problem. So even though the nodes weren't CPU constrained, the way Kubernetes works is there's this process that's sitting there doing that polling loop in every node, and it's responsible for polling all of the things that it's doing, and it didn't have time to poll everything before it needed to go poll again, and so it was sort of getting into the state where it's it's been too long, I haven't heard from this thing. The reason it hadn't heard from that process is because it hadn't asked because it was taking too long. So anyway, a little bit more Python code, alerting. Previously, we sort of alert on errors in an ad hoc way. We wanted to sort of improve that. So we have this library, this is an open source project that we call Datadog Logger. And basically, you have to initialize Datadog, and then you have to configure logging. And then what you can do is when you call this function log, you can't read the comment, but what it says is this causes any error or higher logs to get sent to Datadog. So this adds a log handler that is set to the error level, and so anything that's error or worse, it takes that log message and it sends it as an event to Datadog, and you can add sort of tags. We actually have another library that we use that has all of this code, and it's in a function, and we just call the function once in the beginning, and it configures everything in kind of the standard way. It sets our standard log format and standard tags and stuff like that. So this is nice because now we're creating an event inside Datadog every time an error happens, and we can configure things that way. This is sort of my last slide. The last kind of thing we're doing, and this is kind of an interesting thing, is we're building things that we're sort of calling Kubernetes native applications. The best example of this is our live streaming tool. What happens is when you make a connection to our live processing system, we see that connection, and there's this process, and it gets told that the connection happens, and it goes and it creates Kubernetes resources. It can talk to the API, and it creates Kubernetes resources. And then it creates deployments and whatever, and those things can actually process the video, and then when the stream ends, it can go and say, hey, you're done, and it can shut itself down. This is kind of cool. You can sort of think of it as like fork for the cloud. The problem is Kubernetes is sort of designed with the notion that if the master API server goes down, everything's fine. You can't change things, but everything will continue to work the way it's supposed to work. When you write an application that talks to the master server, if the master server goes down, your application can't do its job. So you have to kind of be careful about isolating this and sort of making sure that it doesn't, cause everything to go down just because your master server went down. Because Kubernetes is definitely designed with the assumption that the master, there is an HA configuration, you can put the master in, but it's designed sort of with the understanding that nobody should be really depending on the master server for like individual sort of web requests and stuff like that. Something to be careful about. But so in conclusion, we definitely like Kubernetes. It has definitely improved, our ability to deploy applications, our ability to develop new applications, get them out there. I definitely recommend considering a SaaS provider, not just for Kubernetes, but also for your databases. And I don't work for one, so I'm not, I don't work for a SaaS database provider. Definitely start small, but start with something real. Like we played around with Kubernetes here and there, but it didn't stick until we were like, this is a thing, our customers are gonna be using it, it's gonna be in production, and it's gonna be in Kubernetes. But it was small. The other thing is automation. We have scripts that automate things. Kubernetes it makes things sort of simple, right? Deploying something is as simple as editing a YAML file. So you don't have to automate everything. You don't have to go in with the understanding that I need to write all of these scripts or tools to automate all of this stuff. You can sort of start with it. Your processes will be a little manual at the beginning, and you can kind of see, oh, this is the thing that takes a while. I should automate this. This thing it's not that hard. We're not going to spend time automating it yet. So that's the end of my talk. Hopefully there's a little bit of time for questions left. We also have a booth if you're interested. We are hiring. So if you want to work on cool stuff like this, come talk to us. Or if you want to hear about our platform, or I think there's some t-shirts left. So does anybody have any questions? I know I went pretty fast through a lot of stuff.
We can start by...
Okay. Yeah.
One of those things of more intelligent questions in the mind. There are many cloud deployment tools out there.
Mm-hmm.
Why specifically do you choose Kubernetes, and can you give some comparison to some other tools? If you can, and please repeat the question.
Yeah, sure. So the question is, why did we choose Kubernetes over other tools, and what sort of advantages does it have to the other tools? We liked that it doesn't really prescribe how your application works. That was sort of one thing. The other thing is it's an open source project that anybody can run, and there's a bunch of sort of different, you can run it yourself if you need to run it yourself. You can find different vendors that run it. Different vendors support different cloud vendors. It felt flexible. We didn't feel like we were locking ourselves in. If you go build out a bunch of Amazon CloudFormation templates to manage your servers, guess what? You're going to be stuck in Amazon until you rewrite those CloudFormation templates. With Kubernetes, it didn't feel that way. We also like the sort of declarative nature of saying, this is what I want my application to look like. I'm declaring it at a high level. There's an application that has these port numbers that need to get exposed. These are the configuration values, sort of the level that programmers think. And you just sort of tell Kubernetes about it, and it makes it happen. So that was kind of the nice thing about it. Compared to other tools where maybe they're not as good at that, or they sort of require you to write your application in a particular way. Things like Heroku, you don't get to decide how you inject configuration into it. It's environment variables, and if you don't like it, tough. Are there other questions? Yeah?
You specifically mentioned keeping your database separate,
Mm-hmm.
and you touched on Redis. I'm curious about things like Redis or Memcache or other things with state. How do you
Sure.
manage that with Redis?
So the question was Redis and databases and things with state and inside Kubernetes. We generally use a SaaS provider for Redis. They exist. And there's a lot of them that you can, the Redis instance is running inside the exact same data center and availability zone as your application. So it's as if you were maintaining it yourself, you just don't have to maintain it. There is one application where we are actually running our own Redis instance. We're only using PubSub, which doesn't support clustering anyway, and it doesn't support writing to the disk anyway, so we don't have to worry about, there's nothing, we couldn't get anything better out of it because there's nothing to back up and there's no way to configure it in an HA mode anyway, so let's just run it ourselves, and it's just a deployment with an instance of one. If you really need to run a database inside Kubernetes, there's these things called stateful sets, and basically they change how the application is run in such a way that every instance of the application knows that it's the first one or the second one or the third one, and so they can sort of find each other more easily. If you think about like Zookeeper, where you need to sort of say, I'm Zookeeper and my ID is 5, and there's one Zookeeper 1, 2, 3, 4, 5, 6, 7, and these are the peers you should connect to. Stateful sets make that easy. And you can also do volume mounts, so you can get block storage from your cloud provider, and then you can back up your block storage devices, but you have to back them up. Other questions? Yeah?
Are you guys using Helm at all?
We are not using Helm, mostly because Helm is for that. It's for, I want to run Mongo, but we don't want to run Mongo, and there isn't a Helm chart for our app, and it's not really useful for us to make a Helm chart for our app because we're the only people using it. Helm seems to be more about sort of sharing sort of standard ways to deploy open source tools more than it is about kind of, it has some features that would help you maintain your, but we've looked at it a few times and it's never felt like it was worth kind of, you also have to run a Helm server to make Helm work. So it's another like thing that you have to run and maintain and it can't go down, whatever. Other questions? Yeah.
The thing you did to deploy locally, is that like a Kubernetes convention or that's just a hack around?
It's our convention. I'm sorry. The question was about how we deploy Kubernetes locally, and whether it's a built-in thing or it's our thing. It's our thing. We kind of made it up. But it works based on a simple Kubernetes thing, which is there's a tool called kubectl. It's how you talk to Kubernetes. And you say kubectl create this file, and the file is a YAML file, and it has a bunch of YAML documents inside it, and it just creates all of them. So that script is like 10 lines long. Kubernetes is really easy to automate in sort of little ways, which is kind of cool. And you can automate it at the shell via the kubectl command, or because it has an API, you can write a Python script and talk to the API. There's Python libraries that wrap the Kubernetes API and stuff like that. That's what we use for like our native applications that actually have to talk to Kubernetes. They're using the Python Kubernetes client. Yeah?
How do you upgrade your clusters? Like newer versions come out every so
Sure.
often.
The question is, how do we upgrade our cluster? And in Google, there's a button and it says upgrade and you press it. I mean, that's why we picked it. I mean, to be totally honest, that's why we picked it. There are ways. It is possible to upgrade. The procedure is you upgrade the master server, and then the master server is always supposed to be backwards compatible. So then your nodes continue to function using the old version, and then the Kubernetes master is at the new version, and then you go to each node. There's a way to sort of take it offline. It sort of moves all the work off of it, kills all the pods, make sure they spin up somewhere else, and then you either destroy the node and spin up a new one with a new version if you're doing sort of stateless stuff, or you upgrade the software and then relaunch Kubernetes. And you just sort of do that one node at a time. So it is possible to do, and there are tools that automate that if you're running your own Kubernetes. But if you use a SaaS provider, they usually have a button. I think we're out of time. So thanks for your time and thanks for your questions, and feel free to find me if you have any more.